Okay, here we go. Okay, now let's go to equal variance is not assumed. Okay, whoa, degrees of freedom. What is that equal to? It's equal to the variance standard deviation squared over n1 plus the standard deviation squared for group 2 over n2. Take that whole thing and square it, divide it by so on and so forth. It's kind of a pain in the butt to work that out, right? Sometimes what people will do to avoid doing that is that they will take a super conservative approach and say that the degrees of freedom is equal to the smaller sample size minus 1, which would be 8 degrees of freedom. What did it turn out the degrees of freedom really were? 14, right? So degrees of freedom 8, it's gonna be much harder for you to reject the null hypothesis. The good news is that you know that the degrees of freedom that you chose is so conservative that if you reject the null hypothesis, you would be right no matter what it was actually calculated out to be, because you took such a low number for that for the degrees of freedom. The downside is that in this case, for instance, you would have failed to reject the null hypothesis because it was so close, right? It was 0.46, 0.046 or something like that was the p-value, right? The t-score that you would have needed for a sample size of it. In other words, we had what was the t-score again that we wound up getting from SPSS and from our calculations? It was 2.18, right? And what would have we needed if it was 8 degrees of freedom? It would have been, we would have needed to get 2.3. Right? Well, at 2.3 for 8 degrees of freedom, right? Okay, so we would have failed to reject the null hypothesis when we could have, when we should have been able to, because we took that shortcut. So, make a long story short, if you're doing this calculation and you try that shortcut because you can do it very quickly, right? If you reject the null hypothesis, you're fine. You don't have to go back and do that nasty calculation. If you don't reject the null hypothesis, well then you really should go back and do that calculation to figure out whether or not, well, maybe had I actually calculated accurately degrees of freedom, I could have rejected the null hypothesis. Okay, or you could just simply go to SPSS and have it calculate the degrees of freedom for you, which is 14.428. Let's take a look. What's our critical value for 14.428 degrees of freedom? Well, it's around somewhere around 2.1, 2.13, and we were at 2.18, right? So that shows you we could have, if we had calculated that 14 degrees of freedom, we would have rejected the null hypothesis. Okay, but it could take you a little while to do that calculation on a test, couldn't it? So a good way to do that is first try the shortcut, see if you can reject the null hypothesis with the shortcut, and you're done. If you can't reject it, then maybe consider using SPSS, or as a last resort, actually do that calculation. Because I took the smaller of the two groups, in this case they're both the same size, 9, and subtracted 1. I used 8 for the degrees of freedom, right? Both sample sizes were 9. Remember when we assumed equal variances, what did I use for degrees of freedom when I assumed equal variances? I added the two samples together, 18, and I subtracted, right, 16. When unequal variances, what did I do as a shortcut? I took the smaller of the two groups. Let's say one was 9 and the other sample size was 12. I took the sample of 9, subtracted 1 to get 8, right? And used 8 degrees of freedom because I knew that was really super conservative. Okay, it's not the right answer, but it's just an easy, quick way for you to test. If you reject the null hypothesis, you know that because the sample sizes are both bigger than 9, or both 9 and larger, right? You know that your degrees of freedom is going to be higher than that number 8. So you know if you could reject for 8 degrees of freedom, you'll be able to reject when you actually calculate it. Okay? Okay, so now Do you really need to understand every word I've said here? No. Well, why am I saying that? Because a lot of this is routine, right? A lot of this is going through the same calculation. You're following a slightly different procedure. We're going through each one of our steps. We're first analyzing, what do I have here? Do I have a single sample test? Or do I have an independent samples test, two sample tests, right? If I have a single sample test, I know what I have to do. I have to decide whether or not I know the population standard deviation or I don't, z-test or t-test. If I have two samples, right, what do I have to know? Are the variances equal or the variances different? If the variances are equal, my degrees of freedom are n1 plus n2 minus 2. And now my standard deviation gets a little bit complicated because I got to calculate a pooled standard deviation and use that in my formula for the t-test. Okay, and that's on that piece of paper. You can go through step by step. Okay, now if they're unequal, well, if they're unequal, I don't have to bother with a pooled standard deviation because they're different. So I don't calculate a new standard deviation. I use the standard deviation for each of the two groups, except now I got a complicated formula for degrees of freedom, right? So I'm always doing the same thing. Null hypothesis, determine what our level of confidence is going to be, what level of type 1 error we're willing to accept, 0.05, alpha equals 0.05, usually. Then do my calculations for my mean and my standard deviations, then decide, well, now how do I apply my t-test and my variances and so on and so forth, then calculate my t-test, then see if my t-value exceeds my critical value for t, which is based on the degrees of freedom. Okay, step, 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 step. Okay, so if I gave you one of these now, you would be able to kind of step through these things and kind of analyze it. You know, they use the word when computer when you write computer programs, or when in language too, they use the term parse, which means they give you you get a big complicated thing and you break it up into steps. You know, what's this? Where does this go? Where does the noun go? Where does the verb go? And so you parse it up into different steps. We're doing the same thing here, right? We're taking the information we're getting in a problem and we're fitting it to the procedures that we're going to use to solve it. And if you can just do those basic things, you won't have too much of a problem. I got some questions online. Let me just take a quick look. Sorry, can you repeat why we choose to use the results that assume variance is equal, and when we use the results assume they aren't equal? Judith, I don't know how long ago you said that. Have I already answered that question, Judith? Still there? You guys online still there? I answered it sort of, she says. All right, I'll go over that one more time. Okay, so now here's two groups, male and female, right? Now I can analyze this two ways. First of all, I have two separate groups. They're independent samples. I'm going to calculate a t-score based on the information that I have right here. First, I'm going to calculate the means for the first group, the males, and the second group, the females. So I have x bar 1 minus x bar 2. I have the top of my formula for the t-score. Now I have to divide that by the standard error, right? Difference between the two means over the standard error is going to be my t-score or z-score when I'm doing a single sample test and I happen to know, I happen to be able to apply z. The bottom part gets complicated. The bottom part depends on my standard error, depends on whether I make the assumption that the variability, the standard deviation of this group is the same as the standard deviation of the other group. If I assume that the two standard deviations are equal to one another, I calculate a pooled standard deviation. And that whole procedure is outlined on that sheet that I put on Blackboard. Let me see if I can't get back to it now. If I could remember the function keys, I need to do this. Let me see, function. Nope, wrong one. Nope, that's the wrong one. I can't get to it. Let's see. Maybe it's option. Nope. Okay. I'm going to have to find it the hard way. Where is it? It's a PDF file. Maybe I closed it. I must have closed it. Okay, let me go back to here and open it again. Oh, there it is. Okay, so remember, the first way, equal variances are assumed. That's the first thing I did. So what do I do there? Since I'm assuming the variances are equal, I have to calculate a pooled standard deviation. Everything I need to calculate that is already known when I calculate the means of the standard deviations for the two groups. The pooled standard deviation is equal to the sample size 1 minus 1 times the standard deviation of group 1 squared plus sample size 2 minus 1 times the standard deviation for group 2 squared over sample size 1 plus sample size 2 minus 2. Everything you need to know, you know how to calculate. Correct? Everybody agree you know how to calculate that? Yes? Right? Okay, so that's your pooled standard deviation. To calculate the t-score, how many standard deviations apart are these? Are they far enough apart for me to reject the null hypothesis? Calculate the t-score. You calculate x bar 1 minus x bar 2, the two means, the difference of the two means, divided by the standard error. Now the standard error is calculated as the square root of it says S1 squared and S1 squared. It should really say SP squared and SP squared, right? Because that's the same. We're using the same standard deviation now for both since we calculated a new pooled one. So this standard deviation pooled squared over N1 plus standard deviation pooled squared over N2, add them together, find the square root, divide that into the difference between the two mean, and it gives us a t-score. If that t-score is bigger than the critical value of t, we reject the null hypothesis. How do we know what the critical value of t is? We go to the t-table, we look up the degrees of freedom. In this case, for equal variances assumed, the degrees of freedom is n1 plus n2 minus 2. In this case, it's 9 plus 9 minus 2, or 16. We look up what the degrees of freedom is. I forget what it was 2.14 or something like that. And we compared the value of t that we calculated, 2.18, to 2.14, and since our value of t is bigger than the critical value, we need to reject the null hypothesis. We reject the null hypothesis, accept the alternative. Okay, step by step, just one step, one baby step after another baby step, one after the other, and eventually you get to the end, you get the right answer. Okay, now what's the difference now with unequal variances assumed? Unequal variances assumed is actually, in some ways, it's easier to calculate t, isn't it? Because t is just equal to x bar 1 minus x bar 2 over the standard error, except this time we don't calculate a pooled standard deviation because the two groups have different standard deviations. We don't have an excuse to pool them together. So S1 squared, standard deviation of group 1 squared over N1 over its sample size 1, plus standard deviation squared for group 2 over the sample size for group 2. Add them together, find the square root of it, divide it into the difference between the two means. Okay, we actually just work out that formula. But we know all those numbers, right? X bar 1, we know that number. X bar 2, we know that number. S1, we know that number, so we know what it is squared. S2, we know that number because we know how, and then we know how, and the sample size 1, sample size 2, we know. Now, this formula here, now that we got our t-score, we have to do the same thing again. We have to compare it to the critical value. Critical value, we go to the t-table. We go to the t-table, we say, okay, for this critical value, for this degrees of freedom, this is what the t-score is that I have to exceed. Except it's complicated. This is not an easy formula to calculate. You can do it. Is there anything here we don't know in that formula? No, right? We know S1, we know N1, we know all of this stuff in this formula. We could calculate it, it's just tedious, right? You could calculate this and it comes out, who knows what it comes out to? Remember from SPSS, what does it come out to? 14.3. right? If we calculated this, it would come out to 14.3. So 14.3, I would be more conservative. I would use the lower, I'd say 14 degrees of freedom. And the t-score you need, critical value for 14 degrees of freedom for t, alpha equals 0.05, is 2.14. Our t-score we calculate here is 2.18. So I still reject the null hypothesis, right? I just mentioned that, there's a little bit of a cheat where if you don't want to go through this formula, you can just say, what's the smaller group? Smaller group is 9. Okay, subtract 1 from 9, use 8 degrees of freedom. In this case, 8 degrees of freedom would not have let you reject the null hypothesis. Why did I say use sample size minus 1, the smaller sample size minus 1? Because I know that's so conservative that no matter what would happen, no matter what you calculated, the real degrees of freedom would never have been smaller than 1, than 8, right? Then this little cheat down here. So if you can reject the null hypothesis doing this, then you're certainly going to be able to reject it doing this. But if you can't doing this sample cheat, then you can't say for sure you wouldn't have rejected it if you had actually calculated it. So if you fail to reject, you should then go back and actually calculate it, or use SPSS to calculate it. Okay. I'm going to move on. Yes.
So you're not going to always just say, oh, assume a standard deviation that is cool or not.
I'm sorry, say that again?
You're not going to always tell us that to assume a pooled or not pooled standard deviation.
Oh, no, you're going to have to make your mind up on that for yourself.
By using those rules?
Well, there's two ways to do it. You could examine the standard. If you so the standard deviation of one group was 10, and standard deviation of the other group was 43. Does that look like they're equal? No. This one is 1.9 and 2.3 or something like that. And it's hard, there's a big difference percentage-wise, but in terms of like real numbers, it's not that big a difference, right? So, it may be so obvious that you can't go either way. But what's the basic assumption to start off with? Is that they're the same. That's kind of the fallback, the null hypothesis that they're the same, unless you can demonstrate that they're different. Now, there's a couple of situations where this might come up. One is that it's so obvious that you wouldn't have to worry about it, right? The second one is that you just don't know. And if you just don't know, there could be two ways you might decide. One is we tell you, assume equal variances. Or we tell you, don't assume equal. We'll tell you, right? Literally, if we gave you a test, we'd either make it so obvious that you wouldn't be able to do it the other way, or we'd tell you, well, what's the third way? We'd give you the SPSS file, tell you calculate SPSS. SPSS does it both ways. And then you look at the Levine's test for equal variances, and you let that decide whether you use assume equal variances or you don't, right? So those are the three possible outcomes. Now, is it possible we might make it, let's make this one 11, make this 13, so we drive them insane, right? So they don't know which one to use, right? Is it possible we might do that? Yeah, if we were really nasty, we could do that, but we're not nasty. So I wouldn't worry about that too much, right? I think that might be a good rule. That might be a good rule. Yeah. I think that might be a decent rule. Yeah. Right. Okay. However, I think in most cases we're either going to tell you or you'll have the tools, namely SPSS, to do the calculation for you. Okay. Let's move on to the next one. Okay. What else? What have I not covered here? What possible kind of two groups have I not covered yet? What? Proportions, right? Okay. We haven't talked about proportions yet. Same deal. We could have, first of all, number one, you can have a situation where you have a proportion, you're comparing it to a known proportion, right? That's almost like a single sample test, right? But mostly you're going to be comparing two proportions. Okay, so let's take a look at this. Okay, now let's see. What are we going to do with proportions? How are we going to actually analyze proportions? Okay, now we're going to stay null and we're going to do exactly the same, everything exactly the same way we did it before. State your null and alternative hypothesis, determine what your level of confidence is. In other words, what level of type 1 error we're willing to accept. In other words, what's the value of alpha? And then, well, a proportion, we're going to actually calculate a pooled proportion for the two of them. I'm going to show you how we're going to do that. Now, in our practice, we have, as an example, researchers wish to test the effectiveness of a new antiviral drug for Ebola. In clinical trials, 92 out of 200 people taking the drug showed improvement of symptoms, while 64 out of 200 taking a placebo showed improvement. So you have two groups. One group is taking the drug, the other group is taking a placebo. I'm going to call those two proportions, okay, I'm going to call those two proportions P cap 1, right? P cap drug and P cap placebo. Okay. Why P cap? What does P cap represent? Represents the proportion of your sample. Now, let's take a look at our null hypothesis, H null. What's H null going to be? P what? P cap? Should I use P cap in my null hypothesis? No, we're not interested in what we want to decide whether or not the population proportion for people that take the drug is equal to the population proportion that people take the placebo, right? Not P for the drug, P for the placebo, like the mean of the population. We're not, P cap is for the sample, right? Okay, and our alternative, H alt, is P cap, P drug, rather, does not equal P placebo, that there's a difference. Okay, see the difference there between P for the drug and P cap for the drug? P for the drug is the population proportion, and P cap for the drug is the sample proportion of people that took the drug. Okay, what's P cap for the drug? Well, how many people took the drug? No, how many people took the drug? 200. Out of the 200, how many of them did better? 92. So the drug, the 92 out of 200 is the proportion of people that improved taking the drug. They had symptom improvements taking the drug, which is equal to, what's that? What is that proportion? 0.46, right? Am I right? I am right, aren't I? Okay, help me out here. Okay, good. I'm old. I mix this stuff up easy. Okay, P cap for the placebo is what? How many people improved out of the number of people that took the placebo? 64 out of 200. So the proportion in our sample that improved among the group that took the placebo is 0.32. Okay, it looks like the drug is doing something, right? But now we need to prove that. Our null hypothesis is that there's no difference in the population if the whole population took the drug versus didn't. Of all people who had Ebola took the drug versus if they didn't take, if they took the placebo. So we want to see whether or not we can reject our null hypothesis that there's no difference between the proportion of people who improve. Okay, so how am I going to do that? Well, the first thing I'm going to do is I'm going to calculate a pooled proportion for P cap. Okay. Okay. So my P cap pool, my P pooled. It's like a tongue twister here. P pooled is equal to, what's it going to be equal to? It's going to be equal to P1 times N1 plus P2 times N2 over N1 plus N2. That's actually really P cap 1 and P cap 2. Okay, so let's calculate that. That's going to be equal to, I'm going to bring up Excel and do it in there. Okay, let me see if I can't do this somehow or other so I can see both at the same time. Okay, so P pooled is going to be equal to, so let's just look at the formula. It's going to be equal to, P1 was how much, 0.46 times, N1 was, how big was the sample size? 200, plus P2, which is 0.32, times the sample size, 200 again, sample size there, divided by, I'm going to close the parentheses, I'm going to divide by N1 plus N2, which is 400. And I'm going to hit enter. It's 0.39. Okay, P pooled is 0.39. Want me to show you another easy way to do that? Another even easier way to do that is to say, how many people, in group 1 we had 200 people, in group 2 we had 200 people, right? How many people improved in group 1? 92. How many people improved in group 2? 64. Okay, let's add that together. That's equal to this plus this, right? And how many people total? We had 400, right? Well, out of 400 people, 156 people improved. What is that proportion? It's equal to 156 divided by 400 is 0.39. See, that's really all I did, was I combined the two groups into one group to get the overall proportion of people that improved. See, that formula I did before is it's not as obvious what I did there with that formula before. If you look at it this way, it's pretty obvious what we did. We just combined the two groups to get, an average, really an average proportion. Except this way, in this case, the groups are the same size. If they were different sizes, it would be kind of weighted, to accommodate for the sizes, kind of automatically. Okay, so that's how we got that P pooled. Okay, so now what am I going to do now? I'm going to calculate. I got my P values, my P pooled. I'm going to calculate a T score. Now, hang on a second here. When we work with proportions, do we ever use the T table? No, we always use Z. Now, how do we justify that? We justify that with one of our assumptions. What's one of our assumptions about when we take proportions? We assume that we have a certain minimum sample size, right? That the minimum sample size is 30 for each group, and that within each group, that the groups within each group, like in other words, the people that improved versus didn't improve, each one of those subgroups is a sample size of at least 15, right? So in other words, you can't have a sample size of 30 for people that took the drug, but then only 5 improved and 25 didn't, because that's under 15 for one of those subgroups, right? One of the values for that variable, right? So we have to have a sample size somewhat bigger than 30, obviously, if we want this to work. The only way it would work for 30 is if they're both 15. Okay, so we have a big sample size here. They're both over 30, both the drug group and the placebo group are over 30, and within that, both the group that improved and didn't improve are both over 15, 92 and 108. 64 and whatever, 200 minus 30, 136 or something like that, I guess, right? So we satisfy that. Since the sample size is so big, we justify using the Z-score instead of the T-score. Okay, so now what do we do now? We do our usual trick. The Z-score or T-score, whichever one, is equal to the difference between our two means, our point estimates. In this case, they're proportions instead of means, right? Divided by the standard error. Again, the only thing that's really changing here is the way we calculate the standard error. So Z is equal to P cap 1, right, the proportion for group 1, minus P cap 2, divided by, well, now here we're going to get excited. This is going to get exciting now. It's going to be the square root of P cap. Notice there's nothing. It doesn't say 1 or 2, so what is that? That's my pooled proportion, right? And it just says P cap there. So that's my pooled proportion there. So let me see if I know everything here. P1 cap, I know that. That's my 46%. P2 cap is my 30, whatever it was, percent, right? P cap pooled is my 39%, right? 1 minus P cap pools is going to be 61%. Times 1 over N1, which is 200, 1 over N2, which is 200. I have everything I need to know here. So let's calculate it. Hey, hopefully you guys are doing this along with me, so I'm not the only one working here. So let me see here. Okay, so Z is going to be, I'm going to do the denominator and numerator separately just to keep things straight. P is equal to 0.46 minus, what was the other one? How much? 64.32, right? 0.32. Okay, and now I'm going to do my denominator. And that's going to be equal to the square root. You could actually break this up into more steps if you prefer. Okay, 0.39, right, times 0.61, 1 minus pooled P pooled, times 1 over 200 plus 1 over 200. Now I'm going to try and get my parentheses here so this works out right. Okay, so if I do this, it's going to calculate 1 over 200 times 1 over 200, and then it's going to multiply it by this, and then it's going to find the square root. I'm going to put the parentheses around this whole thing just to make sure. Okay, and I'm going to hit the enter key. Ah, shit. I knew I was going to get one. I was going to have a problem. I think I got it. It worked out, right? Did it work out? Maybe not. Let's see. 0.039 times, let me break this up into a couple of more steps. This is equals point. I knew I wouldn't get through the whole night without. Right, it does it look right? Yeah. Okay, yeah, it's just got a warning. It went ahead and did a calculation. So what is my t-score equal to? It's equal to 0.14 divided by 0.04. Excuse me, not t-score. What is it again? Z-score is equal to 2.87. What's my critical value of Z for alpha is 0.05? 1.96. Now, however, if I really want, I can go back into my t-table and look up what the p-value really is, right? In other words, what's the probability I would be wrong if I reject the null hypothesis? So we reject the null hypothesis. Okay, so we did, what have we done here? We did this, we applied this comparison of means to single sample t-tests, whether it was a t-test or whether we knew the standard deviation or didn't, single sample test or its sample size. Then we applied it to independent samples tests, right? Whether we assumed equal variances or didn't assume equal variances, right? We had two different ways to do that. And finally, we applied it to proportions. There's one thing we left out. What is the one case that we left out? I'm going to go to SPSS to show you what the one case is that we left out. Because if I click in there and click Analyze, Compare Means, you're going to see there's one category we didn't get to there. Okay, let's go Analyze, Compare Means. What am I missing here? Paired samples. I got an example of that we're going to do really, really quick for paired samples. And paired samples, we've really already done paired samples. Remember we did single sample t-tests before, right? I'm going to open up my paired samples. I have an example of this also in Blackboard. Here's an example of my paired samples. Here are people that took an anti-anxiety drug. This is the number of panic attacks that they reported over the course of a week. Patient number 2 spent a week on the placebo, a week on the drug, same number. The difference is 0, right? I'm going to calculate difference for every patient after they spent a week on each one of them. I'm going to fill down, okay? So, what did I do there? Equals. Didn't I calculate that? No, I didn't. I just put in a 0. You're right. Yeah. Okay, I'm going to fill down. This should work now. Okay, there we go. Some people improved, some people got worse. For the most part, it looks like they improved, right? Had fewer panic attacks. So now, what I can calculate what the average difference is. What's the average difference? The average difference for these 9 subjects, not randomly chosen subjects, the average difference was about 1.5 fewer panic attacks, right? The average difference was 1.5. Let me think about it. 1.5 more. Excuse me. I should have reversed that. Placebo and drug, because actually, does it wind up being up more? Oh, I reversed them when I calculated it. Okay, so 1.5 fewer panic attacks for the drug group as the placebo group, I think. Doesn't matter. Trust me. The difference is 1.5, right? If there was no difference between the number of anxiety attacks that these patients experienced, what should the average difference have been? 0. So instead of worrying about all of these two samples, these two sets of numbers here, why don't we just analyze this as a single sample t-test and compare it to 0? So what's our null hypothesis? Our null hypothesis is the average difference is equal to 0. Our alternative hypothesis, the average difference is not equal to 0, and now it's a single sample test. And you do it just like the way you would have done a single sample test before. Okay, and if you did it in SPSS, since we don't have a lot of time, I'm not going to work it out by hand, but it's literally a single sample test, just like we did at the very beginning, except that this time around we're comparing it. We're taking that one column of numbers, comparing it to 0, and in SPSS. Let me get SPSS here again one more time. I'm going to say open data and go and let's see. Paired samples. Here are the same numbers. Except this time, let's take a look at the data view now. Notice how I'm displaying it now, right? I'm displaying them side by side because when I click Analyze, Compare Means, and choose, I slipped. Paired samples. Okay, and I go over here. Well, look, it's looking for me to put in two variables: the amount and the number of events for the placebo, and the number of events for when they were taking the drug. Same person, right? A week for a period of time on one placebo and a period of time on the drug, and then the others they're kind of randomized. Some people take one before the other, and so on and so forth. Okay, and I'm going to click OK. It's going to calculate my t-test, but now it's a single sample t-test, right? So for instance, pair 1, placebo drug, notice that it actually calculates the mean difference. Has nothing to do with the actual numbers themselves. It only calculates the difference. Standard deviation for the difference, right? The standard error for the differences. Which was just the standard deviation divided by the square root of the sample size, which was 9, right? So that's 2.68 divided by the square root of 8, the square root of 9, 3, would have been my standard error. And then it calculates a t-score. How does it calculate the t-score? It takes the mean and divides it by the standard error, 1.556, just the way you would have done it in Excel. And standard error is 0.9, divides 1.5 into 0.9, gets a t-score of 1.73. For a sample size of 9, is 1.73 a big enough t-score for you to reject the null hypothesis? No, right? It's not even it's not even good enough for a z-test, right? So we fail to reject the null hypothesis in this case. Right? Okay, let's call it a night. So you guys got the idea? No. No. Oh my God. Okay, so we're having a test this week. So we're going to put up some kind of sample questions for the test. And maybe on Saturday morning or Sunday morning or something like that, maybe Sunday morning, Saturday morning, I'll have a session where we'll review. You get a chance to try those, and we'll review problems like this. You try them first. If you tune in and you haven't tried it, you won't get the benefit of it. You need to at least take an effort and try them, so you know, gee, what did I not do here, right? If you just turn up, then you see me go through the same thing I've just gone through here. It won't fill in gaps for you. In other words, when you go back here and try and do these examples on your own, you may say, well, how did he get this pooled thing? Where did that come from? Right? Well, if you give it a try and you get stuck at that point, then when you go over it with me, you'll say, that's where he got it from. That's where that came up. But you really need to give it a try ahead of time. Okay? I'm losing my voice. And how are you guys on? Are you guys okay on the line on that? What standard do we use to decide when to report you when to use the Levine test and SPSS? Well, if you do an independent samples t-test, SPSS always runs the Levine's test. So I would use it every time. Take a look at it every time and use it to decide whether to use the top line or the bottom line. It didn't do it for this test, the paired samples t-test. Why didn't it do it for this test? Because there's only one sample here. There's only one standard deviation, one sample. So there's no question as to whether or not to use equal standard deviations or different standard deviations. You only have one standard deviation. There's nothing it can be different from. It's not two groups. When do we use the top test? I'm not sure what you mean by top test.
I think she understands.
Oh, okay.
The Levine significance?
Yeah. Oh, we use the top
Same.
test. We use the top test when let me see if I can't go back to it here.
Yeah.
We examine. See these four boxes here. They represent the Levine's test for quality of variance. It's a mathematical test that's doing basically a hypothesis test. Now, just like everything else we do, the initial assumption is that things are equal, that there's no difference. And we want to be able to prove that there is a difference. Okay, so now our initial assumption is that the variances are equal. In other words, the top line is our initial assumption. And the only time we'll reject that and use the bottom line is if the significance, the probability of being wrong by rejecting this null hypothesis, variances are equal, by rejecting is if the p-value, the probability of being wrong, is less than 0.05, just like any other tests we do. So in this case, it's not less than 0.05. So we fail to reject the idea that they're equal, so we stay on the top line. Had this been less than 0.05, we would have rejected the idea that the variances are equal and accepted the alternative that they're not equal, and we would use the bottom line instead. So in this case, we'd stick with the top line. Does that help, Judith?